Welcome back to Robotics. Today we're going to talk about pneumatics for robotics, and this is an introduction only. You won't become an expert about this, but we'll talk about some of the basic theory behind designing pneumatic or air-actuated devices on a robot, specifically addressed towards an FRC robot. So first, some definitions. Pneumatics is basically using fluid power of a gas, and the gas flows under pressure to transmit power from one location to another. A little bit different from hydraulics, which uses fluid power transfer, but your medium is actually a liquid. So this is a gas. Now, the most common gas, obviously, is air, and that's what pneumatic means, is you're going to use pneumatics, and the reason is, first reason is it's relatively simple to control. You can make discrete things that move back and forth or actuate in a line, some kind of a linear actuator, really easily. And the big advantage on robots, like on an FRC robot, is that you can have one power source control many applications. And by that, I mean you can have one compressor and reservoir system connected to several different solenoids to drive several different actuators in completely different directions. So if you need to power a lot of linear devices, pneumatics is probably a good solution for you. It has a reasonably high power to weight ratio, meaning that I can get quite a bit of net power out of the system for the size of the motor that's driving it. And that's by virtue of the compressor storing some energy in a reservoir in the form of a high pressure air. And the last thing, it's really safe. Now, when you talk about safe, it doesn't have some of the inherent risks of hydraulic fluid, like flammability is one, or another one, probably less often thought of, is if I have an air leak, I just leak air on whatever I'm working on. So if you went to something like a food processing line and you had actuated devices on that, air would be a good choice because, again, if we leak air on the food, the medium doesn't get destroyed. But if it was a hydraulic system and we leaked hydraulic fluid on it, we would destroy the product. So it's pretty safe from multiple perspectives. Pneumatics are also typically fairly low pressure compared to hydraulics. So it's rare to see a pneumatic system that's operating over a couple 100 pounds per square inch of pressure. Very common to see hydraulic systems in the several thousand pounds of pressure. So when we talk about typical pneumatic components, this is what we're going to look at. And we'll look at these in the sense of an FRC system. So we always need some way to generate or convert our energy from electrical or mechanical into compressed air. So when we talk about converting mechanical power to air power, really what we're doing is we're typically going from electrical power through a motor to mechanical, through a compressor to air power. We also typically need to store our air power. We store it under pressure, typically a pressure higher than what the system uses it at. We need some way of conducting that air. And I say air conductors, these can be tubes, pipes, two of the most common systems, but that just moves the pressure from where it's stored to where it's needed to be used. And we have some sort of valving or solenoids. This turns the air on and off. It controls both the flow and direction. And then obviously when we get the air to where we need the power, we need some conversion method of converting that air pressure to mechanical movement or mechanical power. So those actuators we're going to talk about are going to be pretty much linear actuators or pneumatic cylinders. You can have a rotary actuator or an air-powered motor, but on robots they're relatively inefficient, so we don't see those very often. And last, we need some sensors in the system. And we need those sensors to tell the compressor when to turn on and off, and to do things like sense power or sense pressure changes in the system. Now, typically, in an FRC system, we have these components: a compressor, a safety valve, pressure regulators, a pressure switch, a storage tank, tubing, solenoids, actuators, fittings, and some electronic controls. So let's look at those one at a time. Starting out with a compressor. This is a typical compressor. It's not the only compressor, but this is a Viair 90C. It runs off of a 12-volt battery. It's typically used in automotive applications, to be honest. Pretty low duty cycle compressor, not made to run continuously. It gets really hot if it is run continuously, but it's turned on and off by switching the power through the software. This compressor is rated, I believe, up to 120 or 125 psi. That's what it will run at. That's its max working pressure. Now, typically you're going to have a overpressure safety valve. This is one type of an overpressure safety valve. Usually it's set right around 120 psi. Our system is set to turn on or turn off the compressor at 115 pounds per square inch of pressure. That safety valve is there in case we have a failure in the electrical controls that does not turn the pump off. What that will do is then port the pressure overboard through the little bleed hole at the top up here. This is one type. There's also spring-loaded blow-off valves that we also use. Now, once we pump up that air, we need to put it into a reservoir, and this is a very typical small volume, I believe it's 35 cubic inch air tank, and the tubes just press fit into the end or the ends. You can use as many of these as you want. You can daisy chain them together. It doesn't really matter. The air doesn't need to come in one end and come out the other end. It's purely for your convenience how you want to plumb this, because it is really just a reservoir of pressure. This stores the pressure, or stores the air pressure at the compressor limit, which is at 115 psi. Now, a couple things. 115 psi is not a real high pressure. It's high enough, though, that if you had a failure of this tank, it would be fairly catastrophic. These things are designed, typically the air systems are designed at about a 2 times safety factor, meaning that these are all rated well above their service pressure. But even with that said, you would never want to impact, drop, or damage this tank. If it was dropped or damaged somehow, you'd want to just get rid of it. Don't keep it. When they do rupture, they rupture violently. Other note is if you have a robot and you're doing battle bots, or even you're doing just an FRC robot, you really want to put this in a place where it's not going to be struck accidentally, because it will get damaged. Now, we do need to have a pressure regulator. I mentioned that the air tank holds pressure at 115 psi, but our system uses it at around 60 psi. So we have a pressure regulator that regulates the pressure in the useful system. So it regulates the output pressure to the devices. The thing to note on these pressure regulators, a miniature one here, which is really, really neat compared to the big bulky one that rotates, the handle up here rotates up and down to increase or decrease the line pressure. But the thing about these things is there is an inside and an outside. In other words, the air needs to flow from the in to the out. If you hook them up backwards, they just leak air. They don't work right. So that's one thing to note when you're looking at pressure regulators. You have to plumb them in the correct direction. Now, in line also, we're going to have some kind of a pressure switch. This is a standard pressure switch for FRC. It is a normally closed switch, meaning that as soon as it hits 115 pounds per square inch of pressure, the switch opens up. And that's a safety device that we use on a lot of compressor wiring like this. And what it means is if the wire is cut or damaged, the compressor turns off. The wire needs to be intact in order for the compressor to run. This is just plumbed in on the high pressure side, the storage tank side, and it turns the pump off at about 115 psi. The tubing we use is a press fit, 1/4 inch outer diameter plastic tubing. It's about 200 psi is the burst pressure, again well above its service use of 125 or 60 psi, depending on which side of the tank it's on. And you press fit this into the fittings. The only caveat here is when you're using this, you got to cut the stuff square. If you don't cut it square, it's probably going to leak. Now, the solenoids we use basically control the airflow, and the way they do that is they'll send a pulse of electricity into pilot a valve back and forth. The valve body itself, the solenoid itself, is right here. That's what controls the airflow, and it goes through basically a manifold. So this aluminum manifold will hold 3 of these solenoids on top of it. And then you have got input and output ports up here, your A and B ports, and then you've got air pressure coming in on one side and exhaust coming on the other. These are the exhaust A, exhaust B. We'll learn a little bit more about that in just a second. So that's a solenoid. So what we are allowed to do there is with 12 volts, quickly turn a pressure on or off to a circuit. Now here's an air piloted solenoid. And what this is showing you is it's showing you that in order to move this little spool valve, which is under pressure, you need to use some reasonable force, and that force comes from the air pressure in the system. So it shows it just moving back and forth. With the solenoid, all that's really doing is releasing air into the pilot valve to drive this spool back and forth. So that's what goes on with an air piloted valve. Now, that's really a novel solution to being able to switch the air on and off really quick, but the caveat here is it has a minimum pressure to operate on. So the minimum pressure to pilot that valve, that's around 30 psi in an FRC robot. It depends on the solenoids you use. Now our actuators come in almost every shape and size. This happens to be a standard Bimba round body stainless steel actuator. And we define these by the bore size, which is the diameter of the piston. The stroke length, that's how long the rod will extend, and then the fitting size. So those are some major determinants about which pneumatic cylinder you're going to use. Other things that you can look at is whether it's double acting or single acting. Double acting just means that it can push and pull. Single acting means it only pushes and it returns on a spring. Or it could only pull and return on a spring too. The last consideration for looking at your piston is how does it mount? This is a pretty standard piston. It's got the ability to mount on the nose with a thread, on the tail with a pin. A lot will also have a thread on the tail as well. So that's a universal mount. So the pressure of the air makes that thing push or pull. Well, obviously for us to connect things, I need to have all these threaded fittings, and these threaded fittings fit into the threaded holes. They pretty much all need to have some kind of a sealant. We typically use Teflon tape. When we put Teflon tape on these threads, a little bit is enough. I don't need to goober it all the way up and down. Too much Teflon tape actually can make it leak. So that's a proper application, maybe a wrap or two in one spot on a thread, not completely covering the whole thing. So every FRC robot has what's called a pneumatic control module. This is the signal that does 3 things. It turns the compressor on and off. So it looks at the pressure switch and says, am I below the turn on pressure or am I up to the turn off pressure? And when I'm at those 2 points, it controls the power. Oops, sorry about that. It controls the power right here to the compressor. So it physically has a relay inside that switches it. Now the other thing it does is, remember I said those electrical pulses to pilot the solenoid? These come from the pressure control module. You will see there's 2 sets of wires for each double acting solenoid, or 1 wire per side of a solenoid. So this can control up to 4 double acting solenoids. Down here at the bottom, the last thing to look at, this is actually how it talks to the computer. It uses a controller area network, or CAN bus, which is nothing more than a serial bus. Those are identified on your robot by yellow and green twisted wires. Now the typical layout, physically of it, looks like this. You'll have a compressor, a relief valve, which is mounted right on the compressor, and then you go into a storage tank, over to your pressure switch and a high pressure reading gauge, Then through the regulator, this reduces the working pressure to 60 psi down here. So this is the working end. That's where we'll connect all of our solenoids, which in turn will go out to our devices. Now let's revisit a couple of ideas. Remember that doing work is nothing more than applying a force over a distance. Now the only component of the force that counts is the component that goes in the direction of travel of the distance. So it's really force times distance. Now when we talk about this in physics sense for a robot, if I'm going to lift 1,000 pounds, which would be a lot, but I'm just using this as a simple graphic. If I'm going to lift 1,000 pounds of force, 2 feet, then the work to do that is that force multiplied times the distance. So we see work in terms like foot-pound or pound-foot, doesn't really matter, or pound-inch, or something like Newton meters. So in this example, if I lift 1,000 pounds 2 feet, I get 2,000 foot-pounds, or 2,000 pound-feet. Now, in pneumatics, the work is the force applied over the distance. And that's really just thought of as the force of the piston pushing or pulling times the stroke of the piston. But that brings the question, how do I calculate the force in the piston? We'll look at this piston in a closed position. On the bottom graphic down here, what you'll see is in the red is you'll see the view of the inside of the cylinder. And here's the piston body. The inlet valve happens to be on the right-hand side, and that's what extends the piston. The retraction valve is on the nose side. That's what pushes against the other way and pushes the piston in, retracts the piston. So that's kind of how that works. So I've got air pressure, whether I'm retracting on the left-hand side of the piston, or I've got air pressure for extension on the right-hand side of the piston. So when I look at the force that I'm going to get out of that, that force is really the pressure of the air pushing against the area of the piston face. The force is proportional to 2 elements. The first element is the area being pushed upon. So if I take a constant pressure, like 10 pounds per square inch, and push on 1 square inch, I get 10 pounds of force. If I double the area, I get 2 pounds of force. Conversely, if I doubled the pressure from 10 pounds per square inch to 20 pounds per square inch and pushed on that same square inch, I would end up with 20 pounds of force out. So for our robot, the pressure is around 60 pounds per square inch on the working side. We don't really change that. And for a 3/4 inch piston, we got to look at what the area is. So let's look at that. Now remember, because there's a rod attached on one end of the piston, the retract side, the extend side is always going to be a little bit bigger, the area. So this is a 3/4 inch piston with a radius of 0.375, and you'll find that the area of the piston is 0.45 inches. So the force of this push is area 0.45 inches times 60 pounds per inch, or about 27 pounds. That's how hard a 3/4 inch piston pushes. So the next question is, how hard does it pull? Pulling is the same idea, except I have to subtract the cross-sectional area of the rod. So if I did the math, I would see the area is pi r1 squared, which is the diameter of the piston, minus pi r2 squared, which is the diameter of the rod. When I do that, I get about 0.4. That's my area from this prior slide, 0.402. We're going to round it to 0.4. So the force of the pulling motion is 0.4 times 60, or 24 pounds. So what we see is when I push the piston, I get 27 pounds. When I pull with the piston, I get 24 pounds, a little bit less. That is inherent in every pneumatic cylinder. It pulls less than it pushes because the area of the rod is not counted in the area of application of pressure to generate force. So the next actual question is, what if I double the piston size? Well, when I double the piston size and I get like 1.76 square inches, I generate 105 pounds of push. When I double that same piston, I get about 102 pounds of pull. So twice the diameter doesn't mean twice the force, it means 4 times, because I get 4 times the area. So 4 times the force. So how much air does that take to extend the piston? That's easier than you think. The air used to push the piston out is the volume of the piston. So if this piston is 6 inches long, it would be 0.45 square inches, the area times the length that it's pushed, or 2.7 cubic inches. On retract, it's a little less, 0.402 area on this side of the piston times the stroke, 6 inches, 2.412. Pretty simple, huh? So that's the idea behind calculating forces for the first part of this video. The second part, we're going to deal with how fast does it move or flow, and we'll look at the different pressure differential. So remember, the area of the piston determines how hard it pushes at a fixed pressure. It always pushes harder than it pulls, and doubling my piston diameter doesn't double the force, it quadruples it because it's a function of the radius squared. Thanks for watching.